Welcome, everybody. This is the Rotary E-Club of Silicon Valley. We are excited every week to bring you stories of people making a difference in the world in all sorts of different ways. We are part of Rotary International, 1.2 million clubs. That's wrong. 1.2 million members in about 36,000 clubs around the world. And we're always into that thing of like, what is it that will allow us to think about the world in a new way and to pursue our goals of service above self in ways that account for new technologies, new ideas. And we have got a program today that's going to hit this in spades. And I am excited to introduce Dr. Ted Zanto. So Ted is part of the University of California at San Francisco, Department of Neurology and director of the Neuroscience Division of Neuroscape, which we're going to hear more about because it sounds like it's in the realm of the wildly cool. He does a lot of work on several fronts, including the focus of today's presentation, Electroencephalography, which, as it turns out, is the name of the punk band I played in high school. Not really. So it is such a pleasure to have you, Ted. And with that, I will hand it over to you. Welcome.
All right, thanks. Thank you for the introduction, Rustin. And it's my pleasure to be here with you and to share my experience with electroencephalography. And so today I'm going to talk to you about this tool, which was invented about 100 years ago. And yet we are still using it today in a number of capacities, which include research use, clinical use, as well as commercial applications. So a little bit of background. If you have not heard of the University of California, San Francisco, that's where I work. And it was founded over 100 years ago. It employs 24,000 people, which makes it the second largest employer in San Francisco and the fourth largest employer in the entire Bay Area, which includes Silicon Valley. UCSF includes 4 schools of medicine, pharmacy, nursing, and dentistry. So these are all advanced degrees. So don't feel bad if you haven't heard about UCSF because they don't have an undergraduate population. It's just advanced degrees. Despite that, they are a top-notch medical school, pharmacy school. They are internationally ranked, and it's consistently a great school to go to. So if you're considering one of these fields, by all means, you should apply. Within UCSF, I work at a center called Neuroscape, which was founded in 2014. It has 37 core members, and it is a translational research center within the Department of Neurology. What that means is that we use modern tools and techniques in order to assess brain activity, how it works in normal and dysfunctional contexts. And we're using these tools and the knowledge that we gain in order to develop new methods to help those that are in need. For example, we are the first center to develop an FDA-approved video game that is being used as digital medicine, specifically a video game that can be used by children with ADHD. So we now have a way to help children with ADHD without having to rely necessarily on pharmaceuticals, although in the end, it's more like a supplement. And this is in conjunction with companies we don't necessarily distribute or sell or do any of these things. We just create interventions, and then if there is opportunities, we're happy to work with corporations or companies in order to roll it out to the broad public in order to help people. So video games is one aspect of the tools that we use, but I'm going to be talking about electroencephalography, which is this. This is a picture of a woman wearing 128 electrodes on her scalp. Each of those electrodes produces a little squiggly line there you can see on the screen. And what that represents is electrical activity that arises from the summation of thousands to millions of neurons simultaneously firing, which enable us to record this electrical activity. Now, here's a little bit of history about EEG. I'm going to note a few things throughout the last 100 years. And what's important to realize is that everything that I am going to highlight is still being used today in some capacity. So electrical brain activity was discovered back in 1875, but it wasn't until 1924 where the first human EEG was conducted by Hans Berger, who was a German psychiatrist. And he noticed that when you are recording EEG, if you close your eyes, you see this large, what are called alpha waves, which is a 10 hertz oscillation. That means the brain is sort of pulsing about 10 times per second. Now, what's interesting about EEG is that you can decompose it into frequencies. So on the bottom here, on the bottom left of your screen, you can see a complex waveform. There's a bunch of little peaks and valleys, but that complex waveform is essentially the summation of two simple sinusoidal waves, which have their own characteristic frequency. Now, using things like a Fourier transform, you can decompose a time series such as this. So on the big blue line around 200 to 400 milliseconds post-stimulus onset, you can see a 10 hertz waveform followed by around 600 milliseconds, a higher frequency, say 40 hertz waveform. And if you decompose that into a spectrogram, you can see on the y-axis is frequency, the x-axis is time, and the color represents how much power or energy is in each of those frequency bands. So you can see there's a big burst of 10 hertz energy, and there's a big burst of 40 hertz activity. All right, now what's interesting is that since the 1930s, when this technique was first really applied to EEG, we have realized that many of these different frequency bands can be attributed to different cognitive functions, and I'll mention more about this later. So a few years after that technique was really applied is when the first epileptic activity was recorded in the 1930s. So anytime someone has a seizure, it's essentially the synchronization of multiple regions of the brain, and you can record it with the EEG, such as what's highlighted here. In the 30s, we noticed that, well, people older than me noticed that the EEG was very random. You could apply a stimulus, like a flash of light or a sound, and every time you hear it, it's the same sound or it's the same stimulus, but the brain activity seemed to be doing something different on every time. Well, that's because there's a lot of noise that needs to be accounted for. There's noise from the environment, such as the lights. Your cell phone could potentially be a source of noise, as well as muscle activity can be picked up by the EEG, and we would consider that noise. Beyond that, even if you're not paying attention to the stimuli, that could be considered a source of noise, because if your mind wandering, that may actually detrimentally affect your ability to record some of these neural signatures of your ability to process the sound or the light or whatever you're trying to assess. So what we see is that if you average all these time series together, you take a whole bunch of epochs and average them together, the noise will sort of wash out or approximate zero, and you'll get this nice, much smoother waveform that we call the event-related potential. And the event-related potential has been associated with a bunch of different cognitive functions, such as expectation or stimulus uncertainty. And the earlier waveforms, as highlighted here, such as the P1 and N1, those are typically associated with sensory processing. And these later waveforms are usually associated more with cognitive processing, like working memory or stimulus uncertainty. In the 70s is when we really started to see a rise in the use of computers to analyze EEG data. And what's interesting to me personally is that this really seemed to be the first time people were applying classification or really machine learning techniques in order to automate the analysis of EEG. And so it was a really largely driven by sleep staging researchers and clinicians who would see that when you are awake, you have a time series here that's very high frequency, low amplitude. But as you start falling asleep, you can see from stages 1 through 4, the amplitudes become larger and larger, and those are representative. If you were to do a frequency decomposition, you can see that this is really driven by delta, these low frequency 1 to 3 hertz oscillations. And then once you get past stage 4 sleep, you end up in REM, which actually looks very similar to awake EEG. So now in the 90s, there's another really important advancement in EEG where the use of dry electrodes become a tool. Now, up to that point, people had generally needed to use a gel or some sort of bridge to conduct the electricity that can be detected at your scalp in order to get it through the hair to the electrode. So these electrodes have little sort of spikes on them that can get through the hair and touch the scalp in order to record the electrical activity. About a decade or so after that, we start to see the rise of social EEG, where multiple people started to have their brains recorded simultaneously in order to understand how people interact with each other. And what's interesting for me personally is that I was actually a part of this experiment. These are actually some friends of mine and colleagues who did this research. Now, a few years after that, the use of these dry electrodes was married with wireless technology. And that resulted in a slew of companies that developed these caps that could be used for recording EEG purposes while you walk around in everyday life. And that also simultaneously gave rise to commercial video games, as well as analog games that could be played. And some of these, if you've never tried, are actually pretty fun. And then in the 2017, there was at least 3 EEG in the classroom studies that came out. And so you can see how wireless EEG really took off, and beyond just for commercial uses, but in the research domain, people are looking at how the brain synchronizes together in group settings in order to understand how people learn and how they sort of pay attention. And today it's being used in largely in a research capacity, but also being used in certain schools to monitor attention. So today's applications include clinical research and commercial. On the clinical side, it's being used to identify epilepsy, diagnose sleep disorders, assess brain death, monitor anesthesia, psychiatric evaluations, as well as assist in tumor identification and treatment. On the research side, which is where my life exists really, is to assess cognition, perception, emotion, motor function. You can use it to assess development and aging, as well as to characterize neurological and psychiatric disorders. And then on the commercial side, people use EEG for brain-computer interfaces, such as to drive wheelchairs or type on a virtual keyboard. It can be used for neurofeedback purposes, which have sort of used for wellness and such. And then, as I mentioned before, it can be used in attention monitoring, not just in the classroom, but companies have used this to monitor attention for, say, long-haul truck drivers to make sure that they're staying awake behind the wheel. Now, one of my favorite applications of EEG is to record the EEG, do a frequency decomposition. So you have sort of the delta band is these low frequencies, then you have theta, which is associated with memory. Alpha is often associated with attention, beta, gamma. These different frequency bands can be associated with different cognitive functions. Now, of course, this is an oversimplification. It's very hand-wavy, but just to give you the idea of what these different frequency bands have been associated with. What I'll do is we'll identify a frequency of interest, particularly one that may be deficient in specific populations, and then we can use that knowledge to apply electrical stimulation using the exact same cap. So this is a picture of one of the devices that we use in our lab at Neuroscape that can not only record EEG, but then it can apply electrical stimulation at the frequency that we believe is needed to help facilitate cognitive function. So previously, we've shown that you can use this technique to improve cognitive controllability across the healthy adult lifespan, from younger adults all the way through the elderly. And this is specifically targeting multitasking, but we believe it can be used for a bunch of different reasons. Other people have shown that it can improve multiple different cognitive functions. Currently, we're also assessing whether cognitive controllability in older adults can be improved in older adults with mild cognitive impairment. And we're doing another study using this technique to improve memory ability, as well as biomarkers associated with Alzheimer's disease in older adults with mild cognitive impairment. And if you're not familiar with MCI, mild cognitive impairment, it's a preclinical stage of Alzheimer's disease. So this is a group of people who are at risk of developing AD. So we're trying to use this technique in order to alleviate the possibility that they may transition to AD. And then with other collaborators, we're also doing a study to also improve cognitive controllability in persons with multiple sclerosis, which is a disease that is oftentimes associated with motor dysfunction, but MS has multiple different symptoms associated with it, including cognitive difficulties. So I just want to thank you all for listening. I hope you enjoyed it. I also want to thank my key collaborators who are helping me conduct all this research, such as Adam, Wanyu, Avery, Kevin, Riley, and of course the funding sources who make all this research possible, such as the National Institute on Aging, the National Science Foundation, National Multiple Sclerosis Society, as well as the Neuroscape Network, which is a group of very generous philanthropists who share in our vision of using modern tools and techniques in order to help those in need. And if you or anyone you know is interested in contributing or even volunteering in our lab or participating in some of our research, feel free to contact us. Our email is right there, neuroscape@ucsf.edu. Thank you.
Thank you, Ted. There are so many questions that follow on so much of this material. And it is so exciting to see the detail that begins to emerge. So, you were talking about, for example, the difference in brain early on, the difference in brain activity between, say, eyes being open and eyes being closed. And that did I understand it right? That when your eyes are closed, there's actually much more activity happening?
Yeah, so this is an interesting phenomenon, specifically in the alpha band. So alpha is thought to be an index of inhibitory control. So remember, the neurons in your brain are not all excitatory. There are a lot of inhibitory activities. Otherwise you're going to be responding to everything in your environment all the time. In fact, the vast majority of what we experience in our world is filtered out, is completely subconscious, and we don't really attend to it unless we actually need to attend to it. So alpha activity is oftentimes associated with, yes, it can be elicited by closing your eyes because you're essentially inhibiting visual activity, but it's oftentimes associated with attentional control, meaning that when you're focused on something, you may show, depending on the region of the brain, you can show a decrease in alpha because that's more excitatory. If you are, ignoring something or not expecting something, you can see an increase in alpha. And it really depends on the region of the brain and the context and a lot of other factors. But yeah, you're right. Alpha is kind of inversely related to, what we would consider
visual stimuli,
activity, right? Because it is activity, but it's really more related to inhibitory activity.
Huh. All right. So looking at that, right? So you think about excitatory activity, and obviously there's noise in the sense that you described it. A lot of different things that could be, electronically, kind of interesting but then there's also just the ability of the person whose brain is being scanned to stay focused on something, right? So it made me wonder, for example, whether as an accomplished Zen monk, for example, could sit there and yield a different set of readings, or someone who has some kind of cognitive challenge related to staying focused, whether that kind of is the opposite effect. Can you speak to that a bit?
Yeah. So actually, so I'm not going to. I personally haven't done some meditation research, but others have, and others actually have recorded EEG activity on monks, I believe in Nepal, and they do see differences in brain activity. I believe it was in higher frequencies, frequencies that are often associated with, perceptual responses, which is crazy because when you are meditating, you're trying to clear your mind of things, and yet these people who are meditating are actually showing activity that's very it's more robust than what you would expect. And so that was a pretty novel finding. Research from our own lab at UCSF, we actually just completed, some of my colleagues completed a meditation intervention where we used a game that we developed in the lab called MetaTrain. And this is, of course, developed in consultation with other people who are more knowledgeable into meditation. And so the idea is that when you are playing this game, MetaTrain, you are essentially focusing on your breath. It's breath meditation, and it's adapting in real time. So it asks how long were you able to hold your breath, or not hold your breath, focus on your breath. Right. And the more you play this game, the longer you're able to maintain focus on your breath, which is cool in its own right. That we can take novice people who don't meditate, give them an app, and show that they can get better at focusing on their breath, which is a form of meditation. But the important thing is that we show that it transfers to an improvement in sustained attention on other tasks. And we can see changes in the brain such that their brain activity was more stable. We used a metric called intertrial coherence, which basically means when you see something, the brain is essentially locked to it more steadily. So every time you see something, as I said earlier, there's some noise in the environment, and the brain may do different things at different times. But by using this technique, this analytical technique, you can show that the brain responses are actually more stable. So it's less variable, and their performance during like these sustained attention tasks were also less variable. So it really indicates that we're able to improve not just their ability to meditate, but their ability to sustain attention, which is a result of their ability to sustain their neural activity.
So I'm glad you bring up the intersection of attention and game. So one of the things that I was fascinated by looking over the Neuroscape site is the volume of research that has to do with gaming. As an educator, I hear people, and in particular, an educator of teens, I hear all the time people say, oh, the teens, they can't focus on any blah, blah, blah. And I'm thinking, you've never watched that teen play a game, right? Because the hyper focus that a lot of gamers seem to be able to draw on is something, that's stunning, right? Is that also a part of your research as you look at the different kind of ways that games can be used by people at different stages in life?
Yes, 100%. We are looking at various forms of games. So one game that I just had mentioned was a meditation app. I mean, you can consider it a game because it's a digital interface that you're doing, and you're being graded, so you're getting a score essentially.
Right.
But other apps that we're assessing, me personally, I'm actually using a rhythm training app. So my background is in music. I love playing the piano. I also play a little sax and tuba, and my PhD was on neurocorrelates of the beat, using the EEG in order to identify when the brain synchronizes with the beat of a song, right? So when you're listening to music, you kind of know when to bob your head, tap your foot, snap your fingers. But my work was to assess, well, what happens in the brain when you're doing that? And it's actually this higher frequency beta to gamma bursting that occurs when the beat is happening. And one of the games that I'm developing right now is we're calling Coherence, which is essentially a rhythm training game, because other people have shown that musical training can improve numerous cognitive abilities, including attention and memory. And what we show is that even just with rhythm training, even if it has nothing to do with like a full-on piano keyboard or a guitar, which would require a lot of maybe reading sheet music and such, without that sort of requirement to learn musical performance just by playing a video game that essentially you're just tapping on the beat. Just by playing things like that, we show that you can improve attention and memory. And what we're seeing is changes using EEG. We can see changes in the brain that relate to these metrics of attention and memory. So we see a more stable neural response. Using, again, intertrial coherence, we can see that the brain is in training to the beat more regularly. You can show that, and we've seen that in terms of memory function. We'll look at the ERP, which I had mentioned earlier, and we can see the P3 of the ERP is actually enhanced, which is a component that I said earlier was associated with stimulus uncertainty, but it's also involved in memory encoding. And so we show that the P3 is enhanced following rhythm training. And we also see that actually, I'm talking about data that's not even published yet, so this is very hot off the press. But we're also seeing increases in the delay period as well by using machine learning classifiers. We can actually decode what information they're holding in memory during the delay period. And post-rhythm training, you can actually improve performance of these classifiers, which indicates that they seem to be encoding this information more deeply in such a way that the EEG can now detect what type of information they're holding in memory.
So many different things to focus on. In thinking about that, one of the things that was so fascinating to me about your presentation is this idea that there are these different frequencies, right? Like there is the different response within the frequencies. This yields a bit of a language related to what's happening in the brain, and clearly the more data you have to be able to try to interpret that language, the better off you are. Is there something about new communication technologies, and I'm thinking, smartphones, apps that would allow you to expand the number of people who are giving you data in some fashion that allow like much more rapid advances in this kind of research? I think of someone in my family who has serious short-term memory issues. There's some serious difficulty she has, not in terms of being able to communicate effectively about any given idea, especially related to long-term memories, but just staying focused and being able to remember in short-term ways. And it would be amazing to have her involved in something like this so that I could better understand some of the things that she deals with. That was an awful lot of info. I mean, sort through that and answer whatever you'd like.
Yeah. So let me see if I answer this correctly. I mean, if she lives in the Bay Area, or even not, she's welcome to come and visit us and participate in one of our studies. So that's why I have our contact us information right there on the screen. Anyone's welcome to volunteer either to participate in one of our studies, or they're welcome to even volunteer to just work in the lab and just learn how we record brain activity, what types of things we're learning. It's just a very fun experience, I think, for a lot of different people. And we take people from all across, the lifespan. We take, I think the youngest we've taken so far are high schoolers to work with us, but, all the way, through however old you want to be, it doesn't really matter. So beyond participating, if you're just looking to get, access to some of the things that we're testing, as I had said earlier, some of the tools that we develop, if they show efficacy, we're in the research business, right? So we're just looking to see if there is a signal there. And if there is a signal, meaning that there is something to this game that may be useful for people, then we'll generally pass it off to someone who has the bandwidth, who has the infrastructure to, run it through a big or full, like phase 3 clinical trials, such as what was done with the game I had mentioned at the beginning of this talk. That game, which is now, I believe, called Endeavor, which was developed through Achille, the company that Adam had helped found. And they basically built this game off of the engine of a game that we developed at Neuroscape. So basically, we'll develop these tools and then hand it off to someone else and say, here, you go ahead and distribute it to the people, because we're in the business of research and assessing potential new therapeutics. We're not looking to, create a full company and, deal with the marketing and dealing with the, the back end data collection and the, full distribution of a product. That's for other people to do. And so right now, the only marketable product that's come out of our lab so far is what Achille is currently marketing. But that doesn't mean that more stuff won't be coming through the pipeline, because, as I said, we just showed with meditation, we're showing that can help. We're showing that rhythm training can help. We have other games that also have, you can go through our website and see all the different papers of different types of brain training games that we can show help different aspects of cognitive function. And I think what's important here is that while I believe that our games are very useful because they're adaptive and they challenge the brain, I still feel like you can still get, some benefits by engaging things such as, just music training. Do you need our specific Coherence rhythm training app in order to reap the benefits of memory training? No, I don't believe that to be the case at all. In fact, tons of people have shown that just standard music training helps. So I think some of the research that we're doing is just validating some of the things that people can do in their everyday lives, such as meditation, such as music training. We've shown the utility of physical exercise. These are everyday activities that people can do, and others, have shown that these are things that can help, and we're just piling on, showing that, yeah, there are choices you can make in your life, things you can do in your free time to help sharpen your brain and keep you healthy mentally throughout the lifespan.
Fantastic. So what I'll do is I'll wind things down and then hand it back to you in a moment for a final word. For all of you who are watching this as a recording on the Rotary E-Club of Silicon Valley website, and we love having you let us know where you're from. Where are you connecting from? Are you part of a Rotary club in some part of the world? Are you trying to keep up a 100% attendance? Things like that, all the kinds of things that are related to being inspired on a regular basis. If so, just let us know. And by filling out the form for attendance, you'll get an email that you can pass along to your club secretary to make up a miss. And we also would love for you to engage in the discussion. So a little farther down the page, you're going to see the discuss forum. And there, our members and guests will have left thoughts about this program and other elements of the meeting, the inspirational video, the passage from Rotary about things happening in the world to improve communities near and far. Let us know what you think. Respond to the thoughts of others. Just engage. This is our opportunity in our asynchronous online environment to be able to bring a lot of people together around some really amazing ideas. So with that, I will hand it back to Ted for the final word.
Well, I really appreciate you having me. It's been a lot of fun, and I hope you all learned something. So thanks. Be sure to reach out if you have any other questions.
And we will add the contact us link to at the Learn More links that are just below where you see this recording on our meeting page. So for everybody, thank you very much for joining us, and we will see you next week.